Okay, folks, this is Todd Coburn of Cal Poly Pomona, Aero 3261, Lecture 16C. This is the conceptual exercises that go with Lecture 16A. So we're just going to kind of look at and reinforce a few of the concepts that we've learned so far. Let's start by looking at this little I-beam. As we can see, this is the same one we saw in the last lecture. So with this kind of beam, once again, what we're going to do is we're going to use our shear flow equation where we're saying Q equals VQ over I. Now what we're going to need is the I of the entire section and the total shear on the section, V, and then we're going to need the Q. So you got to ask yourself, moving from the centroid of the part towards the extreme fiber, what is the Q that is feeding or is going through our nail? So this nail right here, we can see if we cut through the nail, like you take your hacksaw and cut through that nail, what area is further from the CG from this through that plane of where the nail is. So we see that this is the area we need. So our area then is going to be, our Q will be the area times the y bar, which is actually the y minus y bar. So our area is simply going to be 100, which is 0.1 meters, times, what's that, 20 meters, which is times 0.02. That's our area. And our y minus y bar is going to be the distance to the centroid, which is, looks like it's 50 millimeters and 10 millimeters, so it's going to be 0.06 meters. That's our Q. We put that in here, and that will tell us the shear flow at the nails. Now, if you look at this, what we really have is this little piece that's nailed onto this little piece that is also nailed on to the lower flange. So what we have here is nails going along the top like this. Now what the shear flow says is that this equation here, the shear flow we calculate, is the pounds per inch. So what that means is underneath this flange we're going to have, actually I'm going to redraw this, and what I'm going to do is I'm going to draw this flange. Let's pull it up here and we'll draw it looking from the bottom. How can I do that? Let's do it like this. So now what we've done is we pulled that upper flange off, and we can see the little spots underneath looking from under here where those nails are. And when we use this equation, that gives us a shear flow basically that's running. If the shear force is working this way, then we know our romantic little shear stresses are going to be moving along here as they come down the face. So this is going to be the pounds per inch along there, and if we want the total force per nail, we're going to take the VQ over I and multiply by the nail spacing, because half that spacing will feed this nail and half that spacing will feed this nail. So if you multiply that by the spacing of the nails, that will give you, instead of the shear flow, that'll give you the shear per nail. That's how we do this. So what we're going to do is find the equation for the shear force in the upper nail, shade that area. We can see that's our area, and that is the plane where we're going to cut it, which defines the area that we're going to be using in our calculation. So that's the area we need, 0.1 times 0.02, and the y bar will be that 0.05 plus 0.01 going from the centroid to the middle of that area, the centroid of that little area. Our equation then is VQ over I, that's our shear flow little q, times the spacing gives us the total force per nail. That's how it works. Let's say if we now want the shear stress, let's see, we want the shear stress in the section. Where is the shear stress maximum? It's going to be maximum where our Q is maximum, which means at the centroid of the section. So we're going to redraw our piece. We're going to draw the line through the centroid. We're going to need the Q of everything above that. The easiest way to do that is to take the Q of that area, which we already have from the last problem, and the Q of that other area. So we're going to have that 0.1 times 0.02 times 0.05 plus 0.005 times 0.02 times 0.025 to the middle of this. That's our total Q for the area, for the section. And if we want the shear stress, we'll just take that shear flow Q and divide it by the thickness, or our width, which is 0.20, and that gives us the answer. Let's say we wanted the shear force in the lower nail. Well, that is going to mean we're going to be making a section cut right through here, and you can see by inspection this is going to give you, that's the area, and this is basically the exact same answers you had for the first problem here, except that the shear flows will be in the other direction. That's how it works. And there's our equation. If we have a problem like this, we can see now you guys should be getting a little more proficient in doing this. So if we want the shear force in the upper left nail, we look at how that's going to work. So we need to first cut the plane. It's right there. Now the easiest way to do this, since we're moving away from the centroid, is to cut it symmetrically, which means we're also going to cut it there, and we're going to shade this area. So if we use the Q for this area and then apply it to our equation, we've got VQ over I is our shear flow, and times the spacing is the force per nail, but you can see that that shear flow now has two paths. So it's VQ over I times S over 2, since there are two paths for that shear flow, and that gives us the shear force per nail. If we want the max shear stress in the section, once again that will be at the centroid. We'll draw the line through the plane that we need it and calculate the Q of everything above it to apply it into our formula. And now it's going to be VQ over IT. It's VQ over I, but once again we have two paths, or you could say we have twice the thickness resisting it. That gives us our equation. This is one of the most common errors that students will make, is not understanding when you're dividing by 2, because you have multiple paths for that shear flow to go through. For this particular problem, now let's see, we want the shear force in the lower right nail. Once again, we're going to be making that cut. We'll find it's easiest to cut it on the other side as well, since we've got two paths as we move from the centroid toward that area. That's the Q we need, and our shear flow is VQ over I. We have two paths, so we divide by 2 and then multiply by the space and get the force per nail. Piece of cupcake. If we have a problem like this, here we have a bolted connection. If we want the shear force in the upper right nail, once again we're going to draw our line through the plane where we need it, which means we're going to slide that plane right through there. That removes that plate, and then we get the Q for everything above that moving away from the neutral axis, which is the area of that puppy. And then we have, plug into our formula, VQ over I is our shear flow. You'll notice we have two paths because we have two bolts taking that down to the next piece, and our fastener spacing. That's the spacing not between going side to side. This is going into the page as I drew in the other slide. If we now want the max shear stress, we're just going to shade the area going down to the centroid through this plane. That defines our area. Bang, pop, one path, VQ over I, one path, and the width is T, the thickness. And if we have a problem like this, this is similar to what we just saw, but now we have a welded beam. So we can see that that upper plate is not attached at all except through those two welds. Once again, if we want the shear force in the weld, we're going to go ahead and do the same approach. VQ over I, we'll find we have two paths, and then we will multiply by the spacing. That's what we want, but for symmetry we're going to cut that one as well. We're going to now cut that piece off. That defines the Q, which is shown shaded, and then since we have two paths, we're going to divide it by 2. If we want the shear stress at the star, let's take a look at where the star is. Let's see right there. If we wanted that, we draw our plane through the star, bang. We'd shade everything away from the centroid from there. That gives us two areas, that area and this area. We're going to get the Q of both of those added together, and our shear stress would be VQ over I, and then our width dimension is, that's right, the thickness. Bang. And if we have a problem like this, now we're actually going to be looking at these further thin webbed pieces like this where we're going to be moving the flow through and around. And actually, you guys aren't ready to solve this, so I'm just going to hold it there and I will put this on the next lecture. So for this problem, once again, if we want the shear force in the upper left nail and need to shade our area, well, you look at this, moving from the centroid, we shade everything that is moving away from the centroid, which means there's our cut that we need, the blue cut. We're going to make complementary cuts through those other two. We then shade our area. Our equation is VQ over I once we calculate the Q of that. How many paths do we have? That's right, 3. Now we have 3 paths, and that means VQ over 3I times S is fastener spacing. Problem like this, same approach. Our equation is VQ over I. If we want the equation in the lower left nail, we draw our line through it like this. This says lower left nail, but for some reason I drew the upper right nail. So what we're actually talking about here is the upper right nail, I guess. If we're looking for the upper right nail, we just cut this off. We now take the Q of this, which is 0.005 times, what is this dimension? Whatever this width dimension is. I can't read it. That's our area, and then the distance from the centroid of that to the centroidal axis is what we need. And that's our equations. And that's all, folks. This concludes our lecture. We're going to have one more lecture for shear. I'm going to give you a bunch of practice problems on the next sub-lecture, so be sure to look at that. Signing off. Hasta luego. Merry Christmas.